because it'll automatically compress if you're on a slower connection or whatever. The ones on Canvas are just an MP4 file, but they're there with the full high quality details if you need them. And slides as well, as I've already announced a couple times. I always get questions even this late in the semester, like where are the slides and stuff like that. So I've announced it several times. Okay. So remember we were talking about this example of a cars and car parts database. So if you had a cars table with just some key and a name, and a parts table with some key and a name, and then a table that combines them or references them, saying which cars use which parts. And then you have to imagine these are really big tables. Okay, and then we talked about this division operator, which is like given some list of parts B, and I've now kind of changed the name just to make it shorter. A is the cars and parts list. B is now just some temporary list of parts. And I want to know which cars, give me all the cars that use all of those parts. And so the way it works is A has some schema, B has some schema. And in order for A divided by B to work, B's schema has to be a subset of A. And then the result will be basically A's schema minus B's schema. Okay. And so specific examples with real values. So if I want to know like every car that uses just part number 2, it's like all the cars. Every car that uses P1, P2, and P4, there's only one car. Okay, so there's the kind of specific meaning behind this. How do we compose this in relational algebra, since the basic operators in relational algebra are project, select, set difference, and set union, and cross product. Sorry. So we're going to try to work this operator out. First, though, let me kind of just say in more like kind of English terms, like specifically what it is that we're trying to do. So, oh, and sorry, so in terms of these operators and in terms of A, B, X, and Y. So A and B are the relations, X and Y make up parts of their schemes. So what we want is, we want to find all X, okay, because the answer, all we want in the answer is X's. So we want to find all X such that, and I'm going to start using a little like logic notation, so don't be thrown off by it too much, but I'll explain. Such that for all Y in V, okay, that's what that means, honey. I'm sure you've seen these in like 2100. This notation. So for all Y in B, and remember B is the parts that we're interested in, parts list. There exists an XY pair in A. Okay? So that's kind of like the formal definition of what we're trying to do with the division operator. So for everything in B, for every Y in B, we're trying to find, is there an XY pair that includes that Y? Okay, so let's kind of just actually look at that. So let's start with P2. Okay, so find all XY pairs that have P2 in the Y. So there's one, there's one, there's one, there's one. Okay, that's basically every car. But that's not the answer. Every car does not have P2 and P4. That's why this is for all Y. So we have to now look at P4. So here's one that uses P4, and here's one that uses P4. Okay. So, which are the ones that have an XY pair for both? Let's see. So we have C1 has a P4. C1 also has a P2. C4 has a P2 and C4 has a P4. So that's why the answer is C1 and C4. Okay. Now, let's work this out using those relational operators. Okay. So you might be tempted to try to start doing something like an intersection or a union. It kind of comes down to something like an intersection, but so let's just kind of slowly build up how to make the divide operator. So I'm going to start with, I'm going to project x out of A. Okay, that gives me just all the cars. And remember, projection automatically removes duplicates. So this is just going to give me C1, C2, C3, and C4. Just every car. I'm going to cross that with B. Okay. That gives us, so B only contains a Y column, and I'm projecting just the X out of A. So this is X's crossed with Y's. But it's only the Y's that show up in the parts we're interested in. So cross with B, I'm not crossing it with all of the Y's in A. I'm only crossing it with the Y's that we care about. So like P3 and P1 will not show up in this cross product. Now I'm going to actually draw this relation, this full cross product, because we're going to start kind of removing things from it and eliminating it down to see how this works. So here is x, y. I'm just going to draw a table. So this cross product, we have C1, P2, C1, P4, C2, P2, C2, P4. Let me move my equation. Project x out of A, cross with B, is what we're currently working on. C3, P2, C3, P4, and C4. Okay. So what this gives us, this is every possible combination of car and part that we're interested in. It's not every possible combination of cars in all parts, because we are not interested in part 3 and part 1. It's all combinations of cars and just the parts we're interested in. Some of them are not real combinations, right? So some of these, the car doesn't actually use that part. But we can start with this, and we now have a schema that is compatible with the schema of A. So it's union compatible, so we can now start doing things like set difference and stuff like that. Okay, so taking all possible combinations, I'm going to subtract out A, all of A. So all possible combinations minus the actual cars and the parts that they use will result in only the fake combinations of cars and parts, or the ones that are not real. Okay, so if we take that whole table, subtract out A, so let's see, C1, P2 is gone. C1, P4 is gone, yep. Let's see, C2, P2, gone. P2, P4 does not show up in A. So we leave it there. C3, P2 is gone. C3, P4 remains. And the other two, C4, P4. Okay. So that's after subtracting out A. Now what I'm left with, kind of just asterisk these things. I'm left with the combinations of cars and parts that are not real. And what this is basically telling us is C2 does not use part 4, and C3 does not use part 4. So car 2 and car 3 are should not be in the result of the division because they don't use every part we're interested in. Okay, so we're sort of getting there. We're getting to the cars that are not involved in the answer. But I can project out of that. Let me just project X out of that whole table. Now that just gives me cars. It gives me the cars C2 and C3. This is very close to the answer. These are the cars that do not have all those parts. I want the cars that do have all those parts. So there's one more step. How can I get the cars that do have parts P2 and P4?
A minus this?
Yeah, so we have basically A minus all of that, but we can't just use all of A. We need to project just X out of A. So give me all cars. That's what this part is. Project X out of A is give me all cars. And then all of this part is cars that do not use part 2 and part 4. So all cars minus cars that don't use those parts, that's the answer. Okay? So, kind of messy, kind of complicated, but just kind of slowly work through it. You can build up through simplifying by projection, taking out columns, coming up with union compatible sets. Set difference turns out to be one of the most useful operations. And so this will be the most complex operator. Set division is the most complex operator we'll really look at by composing it with the basic relational algebra operators.
So A divided by B, sorry, is that just a name of the column?
A divided by B?
Yeah, there's A, B, and then A slash B.
Oh, yeah. So, I don't know, call this one C or something.
Okay.
This is, yeah, this third relation, this third table I have here, that's a new relation, which is the result of the relation A divided by the relation B. Okay. So, a couple more operators that are, as I said, that's the most complex one. These ones will actually be a lot easier because we've seen something almost identical to them in SQL. Natural join. So, the symbol for it is kind of like a cross product because a natural join is built out of a cross product. But basically it's a cross product with an automatic filter where you only take the rows where the columns that the two relations have in common have the same values. Just like a natural join in SQL. So say you have relation A and B where they both have some key, like card num, in the library. Natural join says, all right, well, all the ones where the card nums match after doing a full cross product, we just take those ones. And just as in SQL, in relational algebra, you don't get two copies of the columns that they have in common. So you you'd only get like one card num because it's redundant to have the other one because they all have the same values. Okay. Theta join is kind of just like a plain old SQL join with a condition. So theta join is same sort of symbol, but then you put a condition in subscript, like card num greater than 12 or whatever. Okay. So the output schema is the same as the cross product. It has all columns from both relations. And this is basically just a shortcut for a cross product combined with a selection on whatever that condition is. Okay. So theta join is directly maps to SQL join with a where clause. Okay, and then renaming. I talked a little bit about this last time, but said we'll get to it. So basically, sometimes you do need to rename things to disambiguate. If two things have the same column name or something. But it's also just useful to kind of make things more readable. Like take a big expression in a C program and save that into a variable. And then you can use that variable in the future instead of retyping that expression. So we use row, the Greek row, and it's just an operator that takes the new name you want to give to something followed by some relational algebra expression. So as an example, let's say I want the serial numbers of all books written by Herbert. So start by, since book author is not in the same relation as serial number, we have to join titles to inventory. So I use a natural join. And then I filter out where author equals Herbert using the select. Project out just the serial number. And then I can just rename it to Herbert serials. Okay. Then I can reuse that wherever I want. So I could do something like Herbert serials natural join checked out gives me people who have checked out a book by Herbert. So remember, Herbert serials only contains serial numbers. So I can do a natural join on checked out because checked out has a serial number column. And there's no ambiguity because natural join automatically removes to just one serial number column. But then I also have name because checked out has a name. Oh no, it doesn't have a card number. Pretend checked out has a name instead of card number. And then I could get the names of people with Herbert's books. Okay. So pretty much just straight translation to SQL here. Any questions? Yeah. Yes, so you can do this renaming in SQL, and sometimes you even have to. And we'll see that shortly. Okay, so I'm going to do a little example where renaming will be useful. So here's the database we're dealing with now. It's back to like students and courses and enrollments. I had to give her my A- just to make the example work, but I don't know, she slipped up one semester. So here's the database we're dealing with, and we're going to work through kind of a few examples. Okay. So give me the names of students who have earned an A or a B. So this will involve a couple of tables because the grade A is not in the same table as the student's name. There will be a join or something. So here's kind of where renaming is useful. First, we can kind of break it down. So let's first of all, let's look at just the enrolled table, which has grades, because I want to filter based on whether the grade was an A or a B. And we can do some filtering there and save it into a temporary. So I'm going to do rename. I'll just call it like temp IDs. And what I want the value of temp IDs to be is we select grade equals A or grade equals B out of enrolled. Okay. And one little thing missing here, I also want to project from that, I want just SID. Okay, so I've now found the student IDs of anyone who's earned an A or a B and saved it into a relation called temp IDs. This is not usually the syntax you'll see in relational algebra for OR. You'll usually see this for OR and this for AND. I'm just going to use kind of the more like C style syntax. Okay. Then what? So I have a relation containing the student IDs of everyone who's earned an A or B. I want to get their names. Any suggestions? Yep.
Project student ID and name of students, and then natural join that with FID.
Okay. So let's project SID and name from students. Natural join temp IDs. Okay. So that will result in a relation containing SIDs and names. If we just want the names, we could project name out of that. Or, alternatively, we can just project name out of that whole natural join. So students natural join temp IDs. So here's temp IDs. I'll just call it TID. It contains just one column with like some IDs in it, which means I can natural join it with students and it will automatically compare those two columns and give me just these rows. Then I just project out the name. Okay? So there are a lot of different ways. Like you can move the parentheses around. You can like kind of factor out the projection, or you can do it inside the parentheses on both relations or something. But, lots of different ways to formulate this stuff. Okay. Students who have earned an A and a B. So this would just be Harry in this case. You might think, well, so let's go back. Our condition was select grade equals A or grade equals B from enrolled. So what if I did like select grade equals A and grade equals B from enrolled? What does that do? Does that work? So grade equals A and grade equals B from some tuple. It's not possible for a grade to be A and B. A grade is just one grade. So we can't do that. We can't really use the AND operator like English would suggest. So here's what I'm going to do instead. I'm going to rename. I'm going to use renaming. So I'll say, give me a relation that is called A's. And what I want that relation to be is just SIDs of people who have earned A's. So project SID out of select grade equals A from enrolled. Similarly, I will make another one called B's. And it's all the same except this condition is grade equals B. So I now have a relation called A's, SIDs of anyone who's earned an A, a relation called B's, SID of anyone who's earned a B. Now I want only the ones that show up in both of those relations. What's the operator for finding the things that show up in both relations? Difference is the one where for finding tuples that show up only in one relation and not the other. Intersect, yeah. So if I do A's intersect B's, that's going to give me a relation containing just one student ID, 2. Okay? Natural join that with students to link it up to a name. And then we just project out the name. Okay? Yep.
So could you kind of just like inline that whole expression, or do you need to use?
Right, so I'm using the renaming thing. You could definitely just, so instead of A's intersect B's, replace A's with that whole expression on the top, replace B's with that whole expression in the middle. Yeah, so renaming in this case is not necessary.
So renaming is, or just, are there cases where it is necessary, or is it just an easier way?
So are there cases where it is necessary? Yes. If you want to select out 2 columns that have the same name from 2 different relations, you have to rename those columns when you, sorry, if you want to project out 2 columns, you have to rename them in your projection. So I haven't really shown the syntax, but you can use this renamer to just rename a column instead of to rename a whole temporary relation. Does that answer your question? Anything else? Okay. So, having that in mind, we can use renaming to make things more readable. We have all these operators now: natural join, cross product, intersect, union, difference, and stuff. I have a couple exercises for you. So we're gonna actually do quite a few exercises here, because you just have to like really think about it and work through it for this stuff to sink in. So same database, and I have 2 queries now. I want to know, give me the course names. So this kind of name of any course that has a student born in 1979 and a student born in 1982. Okay, and then I want names of students taking all courses, which in this case would be Hermione. But pretend we don't actually have the actual data here. We need a general query that will do this. So that one will be trickier, but think about the divide operator to make that work. So take a few minutes with the people around you and work these out. You know what? I have a correction. Sorry, this is or. I want a class with somebody, anyone born in 79 or 82.
Oh, that. animal, and then reading animals. Okay. Go to what again? Go how would you write it down? I forgot. Like like a cute thing. There. Right now we're gonna have oh, actually, we have intersect with the enroll, right? With the NID. But how about the protection of the protection? And then you have to make that interface here in one pattern. This is like really long.
Okay. So who came up with an answer for the first one? Yeah.
We begin isolating the relevant SIDs from the students table via the use of the select and what's the other one?
Select and project.
Yeah, that.
Okay.
And then use the divide operation to remove those SIDs from the enrolled table, then subtract the remaining ones from the enrolled tables, and then isolate the SIDs from the enrolled table by the same two operations.
I heard a divide in there. So this is OR. Divide's not really going to come into play here. There's a simpler way to do it. Anyone? And I kind of want step by step. Like, so select this, project that.
So I started by getting the list of just SIDs from the students by using a sigma date of birth is 1979 or date of birth is 1982.
Okay, so select where date of birth equals 79 or 82. I'll just shorten the syntax there. Okay, out of students. Okay.
And then I projected that SID into a SID's temporary variable.
Project SID out of that and then rename it SIDs. Okay? So we have the SIDs of students born in those years. In either one of those years.
The next I was trying to get the course IDs into its own variable before I projected it. So I took the SIDs, natural joined with the enroll table.
So SIDs, natural join enrolled. Okay.
And then I did a projection of the CID on there so I could get distinct IDs. And put that into a CIDs table.
Project CIDs and rename that to CIDs.
Yeah. And then natural join the CIDs table with the courses table and project the name.
CIDs, natural join courses, and project
Name.
Okay, good. So CIDs, natural join courses. So CIDs in this case is just course IDs. We natural join that with courses. And we're projecting out name. Do we have to disambiguate name? There's name here and name here. We do not, because CIDs only contains course IDs. Courses only contains its own one little name column. So there's no conflict there.
So where we have a natural join, would the intersect work?
Yes, intersect and natural join are very similar. If the schemas are the same, then natural join is an intersect. But for example, right here we have CIDs natural join courses, which are not union compatible, so intersect doesn't work. But we could filter it down further and just get CIDs out of courses, do an intersect there, then like join that with courses or something. But yes, they are similar. Okay. Anyone managed to come up with a solution for 2? Anyone brave enough? Surely someone has a suggestion. Okay, project CID from courses. And divide enrolled by what? By this? So enrolled divided by that. Okay, let's see what we have so far. So we have enrolled divided by just this. Okay, so that is going to give us basically, so we have SID and CID in enrolled. SID is ultimately what we're going to care about. We want students that are in all classes. We have, with just these 2 columns, SID and CID, we have the pairs of students who are taking classes. If we divide that by this, which is every single class, that should give us the students that are taking every single class. So I'm going to do one more thing to this, though. Before doing that, I'm going to project just SID and CID out of enroll, because grade doesn't matter here. Okay, so we take this. So this is kind of like our XY divided by Y. Okay, continue. So project student ID out of that whole thing. That's automatically already done by the divide operator since I added that additional project right there.
Natural join, that was students.
Natural join students, written very poorly.
And then project the name.
And then give us the name out of that. Yep. So that gives us names of students taking all courses.
What's the difference between divide and difference?
So what's the difference between divide and difference? So difference, first of all, the two sets have to be union compatible. And difference is going to remove the things from A that are also in B. Divide gives us the things from A that are paired up with all of the things in B. So it is a big difference, but divide is composed of set difference. They're very different operations in terms of what they result in.
When you projected the CID and SID for this role, you'd be able to get the same answer with power, correct?
Yeah, so why did I do this projection here? That was just to kind of simplify it and make it look more like our cars and parts example, where we didn't have this third column that we don't care about.
Would there ever be a time where that would be necessary to project?
Is it necessary to project that out first? No, you can always just project it out later. This does bring up a question though. Is projecting it out before doing the divide more efficient? And lots of questions like that. If I project before doing a join or a cross product and things like that, yes, you can make these queries more efficient by paring down the data first, especially before doing a join. But the good news is the SQL engine will take pretty much any well-formed query and figure out the fastest way to do it without you having to specifically rearrange things to make them faster. Okay. Yeah.
So if you did do that projection of SID and CID, you would have to project the SID out of that, right?
Yes, if I didn't do this projection here,
But the grade would be thrown away.
yes, if I didn't do that projection here, I would still have to project out, get rid of grade at some point.
So the CID just goes away then. For the division.
The CID is automatically removed by the division, yes.
And you're getting rid of grade as soon as you do the name projection.
So I'm getting rid of grade right here.
Sorry, in the case where you remove that, it doesn't matter whether you have it done because you get rid of grade in the projection.
Right, right. I could, yeah, since I'm projecting just name out of the whole thing at the end, grade's going to be gone anyway. Yeah. Okay. Let's take our 5-minute break now, and then we'll talk about SQL. Really ugly looking and convoluted looking. And when you look at the relational algebra version of that query, it's much cleaner, much easier to quickly see what's going on and kind of how it relates things. That's why relational algebra exists. So if you're having a hard time composing a query in SQL because it's got all these weird syntax rules, think about it in terms of relational algebra first, and then you should be able to kind of just step by step translate that into SQL. It's not always a direct one-to-one translation. So sometimes you just kind of have to think about it and remap things in your mind. So projection. Now I'll go over the most confusing part first. Remember, select means something different in RA than it does in SQL. Project in relational algebra is pick out columns, which is select in SQL. At least it's part of the select keyword. So if we have the projection operator in relational algebra, we just say select all of those columns, kind of just directly maps. If we don't have a projection in relational algebra, you still have to have a select in SQL. So you just select star. Every get information query has to start with select. Okay. And then relational algebra select is like the filtering on a condition, which is specified partly by this where keyword in SQL. So, lowercase sigma condition pretty much directly translates into where condition. Okay. Now renaming. So this becomes even more important in SQL, and you have to do it in certain cases. It forces you to. So this from patrons P. So select p.cardNum from patrons P. Patrons P is saying I want to rename patrons to just P. And then I can now use P in the rest of my query, which is just a shortcut for patrons. The interesting thing here is I can refer to the variable before its definition, unlike in a programming language. Okay. So, any questions here? This will become important. It's called a range variable. Okay. You'll see this a lot, even when it's not needed, just to make queries shorter. So rename things to like little single letter relations instead of their full name. So that's one form of renaming. So this is like temporarily renaming the relation. I can also rename the result of a temporary relation, the result of a query. And this lets me nest queries. Okay, so find the serials of all the serial numbers of the Lorax, copies of the book of the Lorax from our libraries agreement. So select serial from, and then the thing I'm selecting from is a temporary relation that is the result of a query, which is select ISBN from titles, where title equals the Lorax, and then I use the keyword as. Whenever I have a nested query like this following a from, I have to give it a name. So this is where SQL forces the renaming. Even though I'm not using the name, so this Lorax here, this temporary name I'm giving it, I'm never using it again. But I have to say, I still have to give it a name. So select serial from the ISBNs for the Lorax, natural join with inventory. So let's just kind of break it in. Forget the top line, the select serial from. Let's just look at the next two. So we have this temporary, give me just the ISBNs for the Lorax. Okay, that's going to be a relation with one column of ISBNs. Natural join that with the full inventory. So it's just going to say, all right, there's an ISBN column in common. It'll automatically filter just the ones with that ISBN. Then that top part, the select serial from, is going to project it down to just the serial numbers. Okay. Now you're probably thinking there's a more straightforward way to write this. You know, you could just do select serial from titles natural join inventory where title equals the Lorax. This is just showing how we can put temporary queries into a name, and this will become useful where you won't really be able to see a way to do it without this rename. Third question. Yeah.
So when I read this, it was almost like it processed the first two commands and then said now we're going to inventory. How do you know which?
Yeah, so it's kind of like do this first and then select something out of that. How do you know what it will do first? It's always kind of think of it as like inside out. And the database engine is automatically going to figure out the right order to do things that will make it the fastest. Basically, you rarely have to worry about order in SQL queries. But you can, most of the time, think of the first select word as being like the final step. So the first word that shows up is actually kind of like the last thing that happens. Okay. Cross products. So these pretty much just map to joins. There are different kinds of joins. So a plain old relational cross product is just a plain old join. with no condition. And a natural join in relation algebra is a natural join in SQL. A conditional join is just a join so-and-so where condition. So pretty straightforward mapping there. In relational algebra and SQL, a natural join will automatically remove the duplicate columns. Okay. So pretty easy there. Okay, what about union? So a relationally union on two relations maps to the SQL keyword union. Pretty easy. So here's our little like corporate locations versus retail locations example again. If I just want to find all locations that this company has a presence at, we in relational algebra would do corporate locations, which is union retail, and then just project out the address. Okay, it looks a little different in SQL. So I have select address from corporate locations, union, select address from retail locations. A union has to operate on two selects. You actually do have to have both selects there. So this looks like it's formulating it in a different way, where in relational algebra, it would be like if I put the projection on just one of them, union, project address out of the other one. SQL kind of forces you to do it this way, where you do actually have to have both of those selects in your query. Okay, so now that we're on to actual SQL, here's my little sandbox. I have like table 1, 2, and 3. Those are just the ones we were messing around with, like adding foreign keys and stuff the other day. But I've added corporate locations and retail locations. So let's just like look quickly what's in there. Okay, basically the same stuff from the slide. And they have managers for each of those locations. So if I want the union of them, you might think, so let's try like select address from something like corporate lokes, union, retail lokes. Doesn't work in SQL. Union has to be in between two selects. So I'm going to select address from corporate locations, union, select address from retail locations. Okay. And it gives me all of the addresses. There were 6 total, 3 in each table, but the union only has 5 because one of them was a duplicate, and a union is defined to not have duplicates. You might try something like, so maybe it's like select address from corporate locations, union, select star from retail locations. It says the unions have, the things I'm trying to union have a different number of columns. It doesn't work. Okay. Here's something weird though. Select manager ID. Let me just reuse this query. Select manager ID from corporate locations, union, select address from retail locations, and it does work, even though those two things are definitely not union compatible. So what is the type of this column in this relation? I don't know, and this is something you should probably never do, even though SQL lets you do it. It can occasionally be useful to like work around some weird things, but pretend that it doesn't let you do this. Okay, let me go back to the actual union. I can also do union all. And then it gives me the duplicates. The reason SQL provides that is because removing the duplicates is expensive. So if you somehow know that your 2 tables do not have duplicates, and and you can safely union them using a union all, it'll be faster. Or if you just don't care, when your output has duplicates in it, union all is going to be faster. Okay. Any questions here? Yeah.
You're saying that the union in SQL works even if the schemas are
Union in SQL works even if the columns have different types. They do have to have the same number of columns. But it would be best for you to pretend that it doesn't work if they're not union compatible. Okay, so there's union all, just saying, performance issues when we're actually doing it for real in a real computer. It's all well and good on paper. Removing duplicates is essentially free on paper. Okay, what about intersect? So kind of the same thing. The relational algebra has to be a little different here if we want. So what we want is locations with corporate and retail. We can't just intersect the full relations because the manager IDs are always unique and the intersection would be empty. They are compatible, but it's not going to give us the answer we want. So we project out address, intersect, project out address with the other one. So now it does look exactly like it looks in SQL, and we just use that intersect keyword. Except, that's one of those things that MySQL doesn't support. So remember, intersect is not one of the basic relational algebra operations, and maybe this is why they decided not to support it, because you can do an intersect in a different way. So let's think about how can we formulate an intersect without using intersect. We've seen how to do it in relational algebra. So what I want is, I don't care about manager IDs. I want to find all locations that show up in both of these tables. So I really only care about these two. Okay, so let's pretend for a minute. Let's pretend that I somehow had a relation called corporate locations addresses and retail locations addresses that do not have that other column. If you had these relations with those names, could you devise an intersect using just other SQL stuff that we've seen? Yes, so an example is join them where address from retail equals address from corporate. Or in other words, natural join. So if I somehow had these two tables, a natural join would be an intersection. So all we need is to come up with those two tables as like temporary things that I can then use a natural join on. So I'm going to write a query that will give me one of those tables. Select address from corporate locations. Okay, there's one of those tables. And if I change it to retail locations, it would be the other one. So I'm going to temporarily say, give me that as, I'll call it corp. Okay. And if I natural join that with basically the same thing, but for retail, as retail. Okay. That's basically what we want. However, this is not a complete SQL statement. This is, although the keyword select appears here, I don't actually have a select on anything. I have a temporary relation, natural join with a temporary relation, and then I'm not selecting anything out of that final result. So I still need, finally, at the beginning, I need select, I can just do star, because all it will have in it is addresses. And that gives me the intersection without actually using the intersect operator. Okay, so natural join is intersect if the schemas are identical. Does that make sense? Thought I saw a hand. Any questions? Yes.
I know it's not necessary for this query, but if you were to add on the end before the semicolon, where for I guess corp would just be the address column, right?
Yeah, so where corp dot something.
Equals retail dot GDP.
Yeah, so if I did like where corp dot address equals whatever, yeah, I can add an additional filter here using corp dot. Okay. So there's one way to formulate it using a natural join, as we saw. Here's an introduction to a new operator that will be another way to formulate an intersect that is also useful for other things. So select x from y where x in, and then a nested query. So this nested query is going to result in some relation, and then I want to know, give me all of the things from y where the x's from that are also in the nested query. So this sounds more directly like an actual intersect. So let me just show you a quick little example. So let's do select address from corporate logs, where address in, and then I just have to basically provide a relation. It turns out I can make a relation without even using select. Or sorry, I don't want adder. I want, let me cancel this query. This is going to be garbage. Let me select name and adder from corporate locations, where there's no name. I'm sorry. I want manager ID and adder from corporate locations, where manager ID in, and then I could do select something here, as long as the result of that select is a single row containing the same type as manager ID. But I can also I can just do this. I can just like put values straight in there. So this will give me the addresses from corporate locations where the manager is either 1, 2, or 3. And so 1 and 2 are the only ones. 3 is some other manager. Okay. But you can put a select in there. And notice I didn't have to rename my nested query. And you can't, in fact, rename your nested query when it appears after the keyword in. Just a slight little difference there. And here's how we would make an intersect using that. So select address from corporate locations where address is in, select address from retail locations. So that nested query will give me all the addresses from retail, and then it will filter out the ones from corporate that are where it's combined. It's an intersect. Okay. What about set difference?
You said when you specify the data has to be single row or single relation with all of the same thing, right?
Yes. So after the in, it has to be the nested query that results in a relation that has the same schema as X. Okay, set difference. So find all locations that are corporate only. So I want to remove the ones from retail after starting with just corporate. That's the relational query version. The SQL version is, we can just say not in. So I can say, give me every address from corporate locations where that address is not also in all of the addresses from retail. So select adder from corporate books where address not in all the addresses from retail. Okay, so those are the ones that are corporate only.
So is this another way to do intersection?
Yep, this is just another way to do intersect. And this, maybe since there are so many other ways to formulate intersect, maybe that's why MySQL decided not to support it. Kind of annoying though. I have an exercise here, another exercise, but I don't think we have time to do it. So we do have a few minutes left still. So I'll leave it as a think about it over the weekend exercise. All patrons who have not checked out a book. Okay. So that one is should actually be pretty easy. And then the second one, all patrons who have checked out the Lorax and Harry Potter. That one will be tougher. Try not to think of this one in terms of division. You could solve this by making another relation with the Lorax and Harry Potter, but I haven't told you how to do division yet. So just try to think of it in some other terms where you can make temporary relations and try to figure out how to kind of join them or do whatever to them to get these answers. And remember, project phase 1 is due tonight. And then we'll see you next week.